Yeah, so now I see that it is live on YouTube.
Yeah, but that's, you see it only because you are already have joined the meeting, correct?
Correct. So, but I can copy streaming link and then I can, one person is waiting since I'm the co-host.
Yeah. Yeah, and I did it.
Yeah,
You,
so
you
now
take care of that.
it is live on YouTube.
Yeah, but that's, you see it only because see, but then there is a problem with that thing, no? Because I hear there is a delay.
But I can copy streaming link and then I can, one person is waiting since I'm the co-host.
Yeah. Yeah, and I did it.
Yeah, so
You take care of that. Okay, the problem that I'm finding is, okay, I have to go. There is a problem with that thing, no? Because I hear there is a delay.
So just mute the YouTube thing. If you
Yeah, I can mute the YouTube, but if I mute it on that, will they be able to hear on YouTube?
Yeah, I think it.
Speaker for
just
YouTube.
mute your YouTube. Yeah, there's an option on that, like the mic is there.
And I have already done that, but you can still hear me on everybody on YouTube as well, is it?
I'll check. I've copied the stream.
Okay.
Yeah, but if I mute it on YouTube, what use is that?
You just muted your own speaker.
Your YouTube browser, your YouTube player.
Yeah, so I mean, how do I share my screen? I'm not seeing an option here. Okay.
Then I'll have to make you a co-host. Okay, then you
yeah, please.
I'll make you a co-host.
Yeah, so is it visible properly?
Yeah.
How do I hide this thing? So, Madhukar, is there option to hide this thing? This
F11 on most browsers will hide.
No, this is not in browser, I guess, right? Okay.
This is a browser, right? No.
I mean, I'm not talking about browser. I'm talking about this thing. This Zoom.
No, that's gone now. No,
Okay.
You've shared your entire desktop. So whatever you do on the desktop, you can close and hide whatever windows that you want.
So are you seeing this mute, start video, and all of this thing here?
No, only you are seeing it.
Only you will be seeing
cool,
that.
Cool. Sorry. Okay, I thought that whole screen. Okay, cool.
The problem is when I make a co-host and then you make it full screen, when some people are attempting to join, I don't even see that here. So that's another problem that I find. Okay, if I go full screen, because that window is gone now for me. No. Yeah. It's still, no, at the bottom it is still there. Oh, I'll have to move the cursor, then I see that. Okay. So that's true. So all the people who are co-hosts are able to admit and they'll see that, I think. Yeah.
Yeah, so I just admitted Argadeep course.
Okay. Yeah, the thing is that bottom toolbar will disappear, but you will have to move your cursor to get that.
Yeah, so my screen is visible, right? Completely.
Yeah, your full screen is visible.
All right, cool.
So for the YouTube thing, I think what you can do is you can go live and then copy the link and post it on Moodle.
But what link? What link do I do there? That's what I'm.
So you see this live on YouTube thing on your screen, right?
Now that he has shared the entire thing, I don't even see that anymore.
No, on your Zoom screen, can you see there is a live on YouTube either at the top or at the
yeah.
So if you click on that, it'll say, view stream on YouTube or copy streaming link. So you can copy the streaming link from there.
Oh, on live on YouTube.
Yeah.
Oh, copy streaming link.
Yeah.
Okay,
So you
okay.
can, yeah. So you can go live, you can copy the link and then you can post it.
Yeah, okay, I got it. If, and I mean, where should I post it? I mean, on the chat window, I could post it. No, no, but no, but not that. That I cannot do. So I'll have to.
Moodle. Yeah, either send an email to everybody, all the participants, or Moodle.
Yeah, so I have to do that every time. Yes. So we'll have to wait for some more time. Okay. There are only 4 people on the thing. But that's okay. But if there are co-hosts, then even if then it should not be a problem. People joining in later on, they won't get missed. No?
With 2 co-hosts, I think this is more than enough.
Yeah.
Yeah.
Okay.
So let's start in 2 or 3 minutes, right? Or should we wait for 5 or something?
Yeah, the strength is very low today. Okay. Sahil is there. It's still not 3:30 yet, so let's wait for a few more minutes. Okay, 3 minutes or so.
Yeah.
Okay.
Yeah, sure.
Okay, I think you can start now. We have enough people, and it's also. But I see your full screen. It's just shows 3:29 p.m. Although it's 3:31 now.
Yeah, so I have stopped the sharing for like a while there because people are joining, so I can just yeah.
So there are 9 people. I think you can start now. I'll start recording. Okay, then you can start.
Okay, so we can wait for one more minute, I guess. It's just
Okay,
like
fine.
Yeah.
So tell me when you want. Yeah, as soon as it's 3:32 now.
It started 33.
Okay. Then I will. Yeah, before you start Tell me so that I can. But you can now unpause the recording yourself.
Yeah.
So,
Cool.
yeah.
Yeah.
Please do that.
I did. So you can start the recording, I guess, for YouTube.
Okay.
All right. So I hope everyone can hear me. Am I audible to everyone?
Yes, you are to me. So I assume you are to everyone.
All right. Okay, so I think we shall start now, right? Okay, so let's start. So if anyone has any question during the lecture, so just ask me so we can discuss. All right. So let's start with this. A goal for this, this first part of the course. So we'll start by discussing the fundamentals of neural networks, what is learning in artificial neural networks. Then we will study about the structure of DNN. And in the next lecture, we will look into this learning algorithm using backpropagation and in detail. Someone's mic is on. Yeah, so maybe in the third or fourth lecture, we will we will have a TensorFlow tutorial and in which we will try to build and train a simple DNN. And after that, Madhukar will take these lectures for these two topics. And we will have this, we will see how to model neural networks as DAG and how to model properties of neural networks. Yeah, so one thing that should be made very clear is that our goal is not to go into advanced topic of ML or deep learning. We only want to learn about verification of DNN. So we will look in up to that point that we are done. We can do some good kind of verification, some good level of verification. That's it. Okay, so first thing. So you might all be aware of this buzzword machine learning, of course, and we'll see what is machine learning. So it's defined as not something very mystical. It's just the study of algorithms which allow the computer to learn, to perform some task without explicitly being programmed for it. So it basically means that we should have an algorithm in which provided we give it a data to train it, or maybe there might be some online data in reinforcement learning kind of stuff. And the point is that the algorithm should somehow tweak itself, its insight, or let's say data somehow that it can perform the same task better. So this definition by Tom M. Mitchell, which is usually mentioned, so it's also in Wikipedia. So a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at task in T as measured by P improves with experiences E. So this is kind of a mouthful. So let's just try to understand it. So with an example. So experience E, let's say the experiences is stock market trends. So our program is getting stock market trends, maybe via internet, or we are just manually typing it or giving it as input. And our task is to predict a particular stock's price. Now, what will be the performance measure for this thing? So it could be this is just an example. So we can actually take the average absolute difference between prediction and the actual stock price. So if my algorithm predicted 30 rupees per stock, let's say, and the actual thing that came out next day was 40, then the difference is 10. So we are so what we want is that this difference should decrease. So if the difference decreases, then we'll say that our performance is increasing. So this is what this definition is telling, that if we say a computer program is learning, if as we give it more data, then it performs better on the task T with respect to some performance measure P. Okay, so this is just an analogy. So just as we human, with the life experiences, we come to know how to behave or not to behave. And this models behavior. Similarly, in a computer, the training data tells the computer how to behave in certain way. And that is what we call as mathematical model. So a computer given training data creates a mathematical model so that, so what is training data? We will look into that. So basically it's a set of tuples, X, Y, where X is the input and Y is the output. So it should learn somehow that given X, it can output Y, or given X something close to X, it should output something close to Y. So that is what we want. So this is what machine learning is like in a, like the definition at least. So there are three main methods of machine learning. So supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is that you give it a set of tuples of input and output data, and it will somehow figure out what should I do with X so that I get Y as an output. In unsupervised learning, we will just give it a bunch of data and we will ask the algorithm that find some pattern in this. We are not telling the computer that, okay, this is input, this is output. We're just giving it some bunch of points in n-dimensional space, and we're asking that find out some sort of boundary so that we can know where the clusters lies and so on. So this is the basic idea of this thing. In reinforcement learning, there is something that you have few online examples coming in, or some small training, one example, and you somehow learn from that. So we will briefly discuss them in later lecture, but not really very deeply, at least not the reinforcement learning part. All right, so we start with the basic thing, basic of this neural network called perceptron, which is a type of artificial neuron. So to understand that, first of all, we have to look at the biological neuron, because it is the motivation for this neuron also. It's a perceptron. So it has these parts. So let me just make it a second. Yeah. So it has these three parts, like main parts. These are axon terminals. This is axon, and these are dendrites. So these acts as input and from other neuron, and as this input is in the form of ions. So this cell just these connections can be strong or weak, and all of the data, all of the ions collectively are like combined in some way here. So we will not even I don't know how actually this happens. So we just start taking it as a model. So they just sum it up, and it is transmitted via this thing, axon, which is acting like a cable, and it is transmitted to other neurons via these terminals. So the two things that we must understand from this model is that this connection could be either strong or weak. And that will what we will define as weights later. And summing up is just the weighted sum of this. Ultimately, it will become weighted sum. And as we pass it, so if there's a threshold here, that if the total sum exceeds the threshold, only then we will pass the signal to other neuron. I mean, not we will, the neuron will pass the signal to other neurons. So this is what, how we just model this. So there are some inputs, and this is our neuron, and it's giving an output. And so what happens inside this is this. So it takes a weighted sum of all these x1, x2, and xn. So just consider there is a w1 here, w2 here, and wn here. And we add them up together, and then we add a bias to it. And we will see why we are adding a bias. And we apply what is called as an activation function, and we get the output. So this activation function is similar to what we have in the biological neuron, that there should be, it has to be beyond a certain threshold. Only then it is transmitted to other neurons. So the same idea is here, that if the total of this thing, the summative weighted sum and bias is above something, then we output, otherwise we don't. Of course, we have a mathematical function here, so it's just not threshold. It can very well become complicated. Okay, so how do we identify a perceptron? Like if we want to define a perceptron completely, like what it is. So it's basically just weights, bias, and activation function. So if I give you all the weights and the one bias and the activation function, that completely identifies a perceptron. So this is the output if you write in equation form, so y is equal to apply sigma over b plus summation of xi wi. So usually we write this using vectors. So just look at this. So x is equal to x1, x2, x3, or like, sorry, it should be xn. I'm sorry. Yeah. So we just add them up. So they're just in a vector. We just write them in a vector, and then there's a w, and we just multiply them x transpose w plus b, and we apply the sigma over it. So that's how you write just like concisely that what a neuron is doing. So let's see a simple example. Sorry, we'll see this example later. I'm sorry, this slides maybe. Okay. Yeah. So first of all, let's talk about activation function. So as I told you, it's basically similar to threshold, but it's a bit more advanced. So the first example is linear function, which whatever it takes, it just outputs that thing. So this is not at all interesting, and we'll see why it's not interesting later. The second is sigmoid function. So sigma z is equal to 1 by 1 plus e to the minus z. And what it does is that whatever the output is, it will fit it in the range 0 to 1. So the benefit of this is, suppose we want probability out of this neural network. So a neural network can give any output, like a perceptron, basically. It can give any output like from 100 to 1000, but yeah.
Yeah, X is a typo. Correct?
Yeah, actually, yeah, I said Z. Sorry. Yeah, X is a typo. Let me just write it if that's, yeah, it should be Z. Yeah, so it will output a number between 0 and 1. So why do we do this? So there's a reason for this. It is because if we just apply the linear function, first of all, linear function is not enough. Because if you have, we'll see later that thing in detail, if you have multiple layers of perceptron and you just apply the linear function, then all of them are basically just one layer. So they can collapse to one layer. So we do not get any advantage of using linear function as activation function. So we must use something non-linear to, and that's the like the core of deep learning. So if you don't use the non-linear function, then you're not going to learn too much. So we'll see why we use sigmoid function later. And this is something we all know, maybe, ReLU. So it's basically just max of 0 and x. So if the output is positive, then it just gives out that output. If the input is positive, then it gives the input as output. And if it is negative, then it gives 0. So the main thing why this is good is because, so this is also typo, I'm sorry. Yeah, so why this is better in some ways, because it's being used almost like in most of the networks that we are using nowadays, and it's easy to compute. So, and also to model. So we'll see in detail in later lectures. Yeah. So let's come to some examples, and this will basically tell us that, okay, it's just for learning purpose. So we don't actually, it's not very complicated, but we need to know to understand what a perceptron is. So this is example number 1, linear function. Yeah. So we are taking we are using a perceptron to compute an elementary function, which is a linear function. So suppose we have 3 variables, x1, x2, x3, and we want to compute this thing. We can also generalize to n variables easily. So can anyone tell me what will be the weights and biases to create a perceptron for this function? You can unmute your mic and speak if you're still there.
So the weights would be something like 3, 4, 5, and we would have a bias of 1, right?
Right, correct. So we have weights 3, 4, 5, bias is 1. Okay, sorry, I didn't ask you what's the activation function. So I've already written it here, but still, it's linear function, right?
Yeah.
So because we are just calculating linear functions, so we just do this. And so this is x1, x2, x3. We have 3, 4, 5 as weights. We take the weighted sum. It becomes 3x plus 4x plus 5x, 3x1 plus 4x2 plus 5x3. We add 1 to it, and then we apply the linear function, and we get this as output. So this is telling you, okay, so we can treat a perceptron. So a perceptron can actually compute a linear function in n variables. Of course, we define it that way. So now this is a bit complicated, not complicated, let's say a bit non-trivial example. So you can also use perceptron to implement logic gates. So NAND gate is called this universal gate. So all the other kind of gate can be like built from NAND gate. So what's a NAND gate? So it takes two input, X1 and X2, and it outputs negation of X1 and X2. So we can assume that X1 and X2 are Boolean variables, 0 or 1. And we have to output this thing, negation of X1 and X2. So can you give, can anyone tell me a perceptron for this? Okay, so let me tell you that this is a bit like, it's not very complex, but a bit complicated, like a little bit. So if you're not getting it, then it's fine. It doesn't matter. Just if anyone is there, I will wait for 1 minute or 30 seconds maybe. Let's see.
Give some hint.
Yeah, I'll give a hint. So let's wait for 30 seconds and then I'll give a hint.
Okay. Because I didn't get it right away until you showed me.
Yeah, I know that's a bit non-trivial.
So if you're allowed to use an activation function that is something like, that is a constant 1 in a domain and then a constant 0 in some other domain.
Yeah, we can use that. It's a step function, right? Kind of a step function.
Yeah. So if we use a step function, then and if you have like weights like 0.5 and 0.5, then we can set up a step function that steps somewhere between half and 1, from 1 to 0. Then, so step function something like, say, it's 1 when it's less than 0.75 and 0 if it's greater than that. And then the weights are 0.5 and 0.5 and bias is just 0.
Okay, let's try to draw it if you say. Okay, so we have, let me get it. Yeah, so let's call this X1. I'm sorry, I think there's something messed up. Yeah. This is X2. So you're saying what should be the weights? Sorry, please don't mind this.
0.5 and 0.5.
Let me just disconnect it for once. Sorry, just give me 1 second. Yeah, wait. Let me just, yeah, 0.5. So there's some problem with my pad, so I think I cannot write properly. Yeah, so it's not working. Let's just go through it. Okay, so you're saying we have 0.5 and 0.5, right?
Yeah.
Okay, so you know the NAND gates output, like you have to get, if you have 1 and 1, then you have to give 0, right? And everywhere else you will give?
And everywhere else I'll give 1. So I have my activation function.
Yeah.
As it outputs 1 if the input is less than something like, say, 0.75. Otherwise it outputs 0.
0.75.
Yeah.
Okay, so one thing is that usually we don't use this like flipped activation function. Like you are giving 1 on output less than 0.75 and you will give 0 otherwise, right? So it's a bit flipped, but okay, it's like, as I have not said that we cannot use it, so let's go with it. Okay, so I hope that it will work. I don't know, like I mean we can try it out, but let's see if the right answer for this, like because I don't have my pad working, so I cannot write now. Anyway,
but this brings up another question. So I thought the constraint was you have to use one of the 3 activation functions. I mean, in general, are there neural networks where the activation functions can be arbitrary? Can be anyone, you know, is there freedom to choose any kind of activation function? Are there neural networks where the choice of the activation function is so varied?
So we usually don't use activation functions which are non-smooth. So we want a smooth function because ultimately we want to differentiate it, take partial derivatives and all. So we need some smooth function. That's very important. And otherwise it's kind of like you are free to choose whatever you want.
So it has to be differentiable.
Third example wasn't smooth. Right?
Yeah, okay.
So yeah,
I mean, we can probably smooth this.
I mean, continuous.
Yeah, or it can be piecewise differential. That's what I've.
Oh, okay.
Well, yeah.
So ReLU is not smooth, true, but at least for the positive part, it is like straight, right? Its derivative is 1 after all. So
Correct.
we somehow we want that thing that, okay, it should be,
Yeah,
it should have some
piecewise
nonlinear property, but it should be it should have one property that if you take derivatives, then it won't like grow too much. Like we'll see that in detail like next time, because when we'll discuss the gradient descent. Yeah, so let's see. So activation function is this. If you like, if you want to use, this is simple step function. So it is 1 if the output, this is greater than 0, input is greater than 0, otherwise 0. And this is the possible answer for this. So you have x1 and x2, and you multiply by -1. So we're just not using 0.5 or this fractional number just for the sake of convenience. So it doesn't matter. And then you take the weighted sum, and then you add a 2, and you get this output. So the claim is that this is correct. Now we will see few inputs, and the rest you can try it yourself. So let's see. So if I give it 0 and 0, so this will become 0, and you add a 2 to it. So of course it's positive, and the activation function will output 1. So it is correct. If I give it as a 1 and 1, then this will be -1 plus -1, that is -2. When you add the bias, it becomes 0, and the output is 0. So if you try 1, 0, then of course this will become -1, plus 2 is +1, and you apply the activation function, the output is again 1. So yeah, it will work. So you can verify that yourself. Okay, so similarly, so you can, one thing to take away from this is that if you create a layer, too many, like use multiple perceptron like this, then you can implement any circuit, whichever you, because NAND gate is universal gate. So you can create AND gates, and then you can build circuits from that. Of course, we don't do that. It's just for the, like, it's just because we have an AND gate. So it's just theoretically good to know that, okay, we can build arbitrary circuit using perceptron if we want to, but we never do that in practice. All right, so
that defeats the purpose of. Then you could write.
True, we can write simple.
Simulating traditional programming paradigm.
Yeah, true. So we don't need that. It's just for the sake of like mentioning. I just mentioned it. Yeah, illustration. True. All right, so this is not example. It's multi-output. So we just see how can we get multiple outputs out of a perceptron. So this is quite simple, that if you can use 2 neurons, and they will have some activation function sigma. They will have different weights and biases, W1 and W2. So there's a transpose here, I'm sorry. Similarly here. Yeah, and so these X1, X2, X3, these inputs are like shared among all the neurons here. So both of them will get the same input, but they will of course behave differently, and they will output something different, because that's what we want. Otherwise we can just have one neuron. So that is multi-output. So this is what you call as a layer. So this forms a layer. So you can have Y1, Y2, Y3 until like Ym, and then you have an M neuron layer. And now what you can do is these outputs can act as input for the next layer. And you can have as many neurons as you want here, and you can reapply the same thing. So remember, if I have 2 neurons in this layer, then output will again be distributed to this. So one just thing about terminology here, that don't confuse this thing with multiple output. So this is not multiple output. This is multiple output, because here you are just bifurcating or like just transferring the same output to multiple neurons. So it's not different. These are not different output. They're the same output. You're just passing them to all the neurons in the next layer. So that's what you call as a neural network. So we will just see that now. So by joining multiple layers of multi-output perceptron, we get a network which we call as a artificial neural network. So this is the input layer, and this is the output layer, and you connect these these neurons. So this is not like these are not neurons, if you can notice that, because they are just telling us that, okay, we have to pass this. There is no bias in this, and there is no weights for these things. They're just denoting, they're just nodes denoting that, okay, the input is coming and it is transferred to all the neurons in the next layer. Similarly, this is also transferred, and each neuron somehow takes a weighted sum and bias and applies activation function and output something, and the same output is distributed again to the next layer, and so on. So this is, that's all. So that's what you call it as a neural network. And these are what we call as hidden layers. So they are called hidden because if you are treating as a black box, again,
one clarification. I also
yeah.
even a question. So you can have, I mean, input layer, of course, there's no transformation or activation function there. It just passes the inputs, but there are multiple components of the same input. I mean, multiple components, they together form the input. So why multiple nodes in the input layer? I mean, it's just for convenience, I guess. Or you want to decompose the input into several components, but they conceptually they all together form a single input. Correct? When you know.
Yeah, true. So if you treat it as a vector, then they form just that. I think, yeah. So it's just for, let's say, graphical convenience or aesthetics of this, that we just write this is like this. So you can just have one input and just transfer it in some way. But yeah, it's just good to see this thing. So this basically, so what we are saying is these are actual layers. So this is not a layer, actually, this is not an actual layer of neurons. These are the this is one perceptron layer, this is another. And if we treat this whole thing as a black box, then we only give it input and we get an output. So of course, these will become hidden to us. So it's just a name.
Yeah, another thing is the output layers can also have multiple nodes. If indeed, if you're multiple features.
True.
Okay, so
yeah, output can have multiple neurons here to output. But the point is that this is hidden layer and there is nothing too much hidden about it. It's just a name for that. So these are exactly like the output layer. All these layers are similar in structure. There's nothing going on special with these hidden layer or this output layer. Just this layer is kind of useless. So it's not actual layer. Okay. So now we will see what we want is this. So we give it an input and we want that these weights and biases should somehow give us an output which satisfies the condition that we had. So we had a tuple, right? X and Y, and we wanted it that if I give it a X, then it should output a Y. That's what we want. That's what we wanted. So these weights and biases, they have to be managed somehow that this thing is true for.
In other words, Y is the expected output. Okay, so you want as close to the expected output as possible.
Yeah, and both of them can be are vectors actually in general. So we just want that given this X vector as input, they should output Y as close as possible to Y actually. And so let's see. So what is this? This is called as training data. So it's basically a set of correctly labeled. So this is just, I wrote this for, okay, let's see. So it's a set of input output pairs XY. And by correctly labeled, I mean that you can, I mean, for each X, this is what you want as an output. So that's it. That's all that I want to stress from this thing, nothing more. So what is learning now? Nothing actually very fancy. It's just that how do you manage all these weights and biases so that your output is as close as possible to the correct output, or it is in certain range which you want for the output to be in. So that's what learning means. And so we'll use learning and training interchangeably. It doesn't make a difference, just kind of similar two terms for the same thing to a certain extent, yeah. So now let's see. So if I give it an input and it's giving me an output. So this network, if I have some random weights, so of course I cannot expect it to output what I wanted or what I expected. So it will be what we say, there's a loss in this. There's a cost of this example. So it's not working properly. So we have to somehow quantify how much wrong our neural network is doing on a training example. So for doing that, we define something called as cost function. So cost function basically tells you that for a given input, how bad your output is. And then, of course, we take some kind of average over all the output, and our task, the learning, becomes how do you decrease this cost? How do you like find the minimum of this cost function? If not minimum, let's say very close to the minimum. So the cost function is a function of weights and biases. So it's not a function of these inputs, it's a function of these weights and biases. And why is that? Because when I give an input X and Y, okay, so I've already given the X and Y, the values of X and Y are already given. So the cost that we have, the difference, will only depend on how bad my weights and biases are or how good they are. So therefore, cost function is a function of weights and biases. Let's see it in detail. So suppose I have a neural network with two layers. This is hidden layer and this is output layer. And you have X1, X2, X3 as input. And some weights are here. I've not represented that. So let's say this is what I wanted. So on this input, 0.5, 0.6, 0.4, I wanted Y1 to give 0.1 and Y2 to give 0.9. But because let's say the weights are randomly initiated initially, so we just get 0.6 and 0.4. So of course this is bad. So how do we calculate how bad is this? So there are various kinds of log cost function that we can have, but we'll talk about one of them, which is called as mean square error. Of course, I think you all are familiar with it. So you just take the difference and you square it, and you take this difference and you square it, and you add it up, and then you take the average of this. So this is what the loss is for one single example. Now to find out, so our task is not to change or tweak our network so that it performs better on one single example. So if we are doing that, that's not good. Not always, but usually it's not that good to just train a model to like tweak our numbers just to make it better on one single example. So our task is that to reduce the total cost on all the examples. So we take average of all the losses that we are getting for all the training examples. So if I have 100 examples, then I'll calculate the loss for each example, and then I'll take an average of all those loss. And now I want to tweak my weights and biases so that that cost decreases. Yeah. So suppose we have Xi and Yi as one training example, and the output that we get from this network is Y hat Xi. So the cost of this example would be Y cap of Xi minus Yi. This is a norm and square. So norm is basically these are two vectors. So you just subtract them and you take a sum of squares of all the coordinates, and then you take a square root. That's a norm. So you square it again. So basically it's similar to this thing. So this is exactly what we're calculating without this divide actually. So I think we can divide it by that. It's not that necessary, of course, because it's just a number, constant number. Okay, so the actual cost function would be that you take this thing, you take average of all the this cost for all the examples. So if I have k examples, then I add this cost for all the k examples. Sorry, so I divide it by k. So I think maybe I wrote n. Yeah, so I divide it by k, and I get this is the cost. So this, remember, this is a function of weights and biases, and of course CI is also a function of weights and biases. And we will look into this cost function in detail and find out how do we apply the gradient descent algorithm on this in the next lecture, I guess. Okay, so this is the cost. So let's just talk about it for just 2 minutes. So just to recap what we are doing here. So this is a network which I initialized randomly. And for these inputs, I wanted these outputs, but my random numbers, because they are random, they're giving me some weird output like 0.6 and 0.4. And I find out that, okay, my system is not working. This network is not working correctly. I find out how bad it is over all the training examples. And then somehow using a learning algorithm, I'll figure out how to change these weights so that it performs better. Then we change these weights. So first of all, we change these and then we change these. So this is like in some sense, what we call is back propagation. So we just want to find out the weight so that the output becomes closer to our required expected output. And then we apply this repeatedly. like with expectation that, okay, like after a few iterations of this, this loss will become significantly less, let's say to the level that we can accept, to acceptable range of error. Yeah. So let's see like few example of neural networks. So this is some example that we will be doing in detail in next lecture. So this is, this will seem pretty dumb on the first, when you see this. So we have a picture of size 4x4, and let's say it's a binary picture. So you have a matrix, 4x. Yeah.
Before you move on, I have one question.
All right.
Okay, you can choose to answer it now or later. Go to your previous slide. Yeah. So how do you, the question is, how do you choose the number of layers and number of nodes in each layer? Maybe you could address this separately, okay? I mean, eventually, so one decides on the number of layers and number of...
All right, so when we were talking about the next example, I will give a hint that how do we choose that, but it's not at all kind of a precise mathematics there. You just have to use some heuristics, and of course there's some thumb rule that use 2 by 3 the number of input. So if the input layer has n, then use 2 by 3 of n in the hidden layer, and then you decrease it further. So they're just heuristic. I mean, I have not seen precise ways of selecting these things. So people just try out different kind of number of neurons, different number of layers, and they find out that, okay, which one performs best, and they just choose it.
Some examples that I have read, where it's some applications. Okay, of course, I'm no expert on the neural network, or at least for those applications, there's a more split. Okay, so you say number recognition or something. Each, eventually you have to recognize something. I'm using that example. But so you split it up. Okay, if you want to recognize numbers, maybe it has so many segments that make up particular.
Yeah. So let me just tell you one thing.
Determine the thing. So if you could structure your application that way, that is one way. Now, you're explaining it slightly differently, but anyway, that is something that to address. Okay.
Yeah, so this is kind of how we intuitively want to think of neural network, that it's somehow figuring out some features here, then some features here, or some segments of the picture. Of course, it doesn't work exactly this way. So, I mean, in a big network, it's not even possible to understand how it's working. So we just leave it to it that, okay, somehow figuring it all out. But I mean, it's not exactly that it's taking out features one by one in each layer. It's just okay, so I don't have the
important thing is that is not part of the training. I mean, training only adjusts the weights given a particular structure of neural. Yeah.
True. Yeah. So we just want to find out, okay, while we are building a network, we have to define the structure definitely. But after that, the training, the algorithm just changes weights and biases to find out. It doesn't even change the activation function. So it just usually. So it just finds out what W and B should be for all the neurons, so that this cost decreases. Sorry, so I forgot to ask one thing. Is there any question? If there is any doubt, then you can just ask up to this point. So I'll wait for a few seconds if anybody is having any doubt.
So essentially what we're doing is we're trying to guess the weights until we arrive at a set of weights that actually give a answer that is closest to the answer that we want, right?
Yeah, so I will not use the word guess here, because it's just not about guessing the weights and biases. So we initially start with, let's say, normal distribution or some kind of distribution for the weights and biases. We fix it, and then we apply a proper algorithm, which is if there's my minimum, then it will properly find that minimum. So it's like finding a minimum of a function. So this is a cost function, and suppose it's in 100 dimension or whatever, we don't know. let's take one 2-dimension case, and this is the cost. So we just want to go down this slope and find out how close we can get to this minimum. And that's what learning is. So that's why it's called gradient descent. So this is gradient. Gradient basically means derivative. And you are just finding it out that where should I go to minimize this cost over all the examples. So not on one example, I'm stressing it again, not on one example, over all the training example. That's what our goal is. Okay, so anyone else?
Yeah, no, Sahil has some comment on the chat. Sahil, you may want to.
I was just saying that, yeah, the thing you mentioned about some structure being fixed, people usually talk about hyperparameter optimization, which is, for example, deciding the number of layers would be one, but there can be lots of other things. But yeah, if anyone wants to look that up, you can use the keyword.
I see. Okay.
Yeah, so they are called hyperparameters, and of course, like there could be ways to do this, but at least for this course, we will just see you will somehow, as a human being, you will figure out what hidden layers, how many neurons we should use, how many layers, and then our task will be just to find out the weights and biases. Up to that point, we will do in this course at least. All right, so I hope no more questions, right? So let's proceed. So let's look into a few examples. So this is just a binary matrix. So I have a 4x4 matrix. Let's say I put a 1, 1, 1, 1, and some sort of zeros. So I convert that into a picture like here. So if there is a 1, then I make it a dark orange color, otherwise very light. I don't know if it's visible at all, but of course there's something here. So this is a 4x4 picture, and it could be let's say there are 3 shapes: L shape, a square, and a cap. And we want to recognize which of this shape it represents. So of course, one of the ways you can hard code it very easily. So you can write that, okay, if these all indices have a 1 in the matrix, then it's L shape. If all of them have 1, then it's a square. And this is like, of course, this is possible. But we will in the next lecture at least, we will use Python to implement this and find out that, okay, can we do it without explicitly mentioning anything. So given a matrix, our task is to recognize these 3 shapes. So first step is to, like, because neural networks works with vectors, like just single dimensional vectors. So you convert this into, so this is converted into this thing. So this is 1, 1, 1, 1, 1, not 1, something like this. And this is exactly what you write here. So it doesn't matter actually how you write this. There should be just a uniformity in the conversion. Up to that point, if you use columns or rows or maybe even any scrambled version of this, it doesn't actually matter. So you flatten the input matrix to a vector. And then we need to find out weights and biases such that in the step 2, I multiply all the weights and biases and vectors with the weights and then biases, and I apply that activation function. Ultimately, I want that somehow should figure out which shape it was. So this is what we will be building in the next lecture at least. Just, I mean, the initial part, not in the whole lecture. So you have 16 inputs. So it's a 4x4. So you have 16 inputs, and this represents that there are connection to each neuron. So, and there are 6 neurons in this layer, and there are 3 in this one. And so basically somehow what we want is that these neurons should help us recognize which of these shape it is. So ultimately we want this should be, let's say 1 if it is L shape, this should be 1 if it is a cap, and this should be 1 if it's a square. So of course you can do it by hand if you want. So there are 16 by 6. So for each neuron, you have to figure out what the weights are for this neuron, what are the weights for this neuron, and so on. And then similarly, what are the 6 weights for this neuron, and so on. And that's what we want. So we will look into this, and in the next lecture, we will try to implement an algorithm which can find out these weights and biases for us, so that it at least works on these 3 inputs. And to make it a bit more interesting, we can even have a 0.5, 0.6, or like just make this 0 to 1 and have this brightness go up and down. And then we can have multiple shapes. Of course, this is something which you can hard code, but let's see the next example. Like before this, like I'm just telling you. So we have these weights. So there will be 6 of them for the first layer. and you write it as a matrix, and then you multiply this thing with your input, right? And then you will get all these 6 outputs. So this row will multiply with this thing, and you get output for Z1, and then you get output for Z2. So we will actually look into all this in the next lecture and how you find these weights. So I actually wanted to show you the Python code, but I think it's better to put it in the next lecture. Okay, so let's see the example 2. So this is something which all of you are familiar with. So we have some handwritten digits, and it's a 28 by 28 image. So this is available on MNIST.
Hitat, one question I had.
Yeah, sorry.
Did you explain what these outputs of Z1 to Z6 are supposed to be? I mean, do they? I could understand what the 3 things final output is. That it should.
So yeah, so we are just giving it some liberty to choose what they should be, so that it can do this task. We don't know what.
Fix this thing to be 6. Okay. Yeah, and you will have to somehow with 6 intermediate features, you will have to make the decision as to how.
True.
Okay.
Yeah. Okay. So this is a way which we can think of it. So we can see, you can find it out when we'll implement the code, and I'll give you the code. So you can play with it, that if I use 3 neurons in hidden layers, what happens then if I use 4, and if it gets better if you use more neuron or not. Of course it doesn't. Like if you use too many neurons, more than inputs, then I don't even, like, at least in the simple case, it won't make much of a sense, and it will just complicate and increase the time for this application of neural network, this function. So it's one thing to understand here is that all of this is just one function. So it's just a one mathematical function, a very big function, of course, and it takes 16 input and gives you 3 output. And there are parameters, weights and biases, which we have to find out. Okay, so we need to find out these weights and biases so that these 3 can recognize these shapes. So this is 1, if this is that, and so on. Okay. All right, so let's see this example. So this is basically OCR. So this is from Michael Nielsen, this image. And so you have these handwritten digits, and you want to find out which digit it is. So when you see this, it seems like really interesting that, okay, a handwritten digit, and you need to find out which digit it is. But it is theoretically similar to this thing. Like there's not much of a difference in this. Of course, this is too complicated for us to comprehend that what is going on here. And we cannot, at least I cannot hope to find all these weights and biases by hand, or even by writing some program which doesn't use a learning algorithm, so that I can recognize all these digits. But for the previous example, we can find out the weights and biases by hand. But just as dumb or non-intelligent this is, so is this thing. So I mean, I'm just telling you so that you understand, like, just to drive a point that it's not that mystical. There's nothing too much into it. So you just want to find out whether this thing represents 5 or not. And of course, we want this to be 1 and other to be 0 or close to 0, and this close to 1 if the input is if the input image is like a 5, a handwritten 5. So this is a very like hello world of neural networks. So you can find the code anywhere at all. Like, but still, we will. I will guide you through the code in the next to next lecture, and we'll see how we do this. So this is what we want. The output layer will have high value on the neuron, which corresponds to digit whose image is being fed into the input layer. So input layer has 784 neurons. And of course, you can figure out how many weights and biases there will be. So there are 15 neurons in the hidden layer. This is arbitrary number, like kind of an arbitrary number. Like you have, as Sahil said, that we can have some tricks and ways to find out how many neurons to use, how many layers to use. But in this example, at least, just arbitrary. So we have 15 neurons, and so 784 into 15 plus 15 into 10. So that many weights we have, and similarly 15 plus 10 biases. So there are bias for all of these, 15 biases for this and 10 biases for this. Of course, there are no biases for this because these are not neurons. Exactly, they're just nodes. Okay, so this is what I wanted to describe in this lecture, at least. So let's just see how, so this is just an overview, how we find out the right weights and biases. So I have maybe mentioned it earlier. So we create matrices of weights. So for each layer, we have a different matrix, which represents all the weights here. And then we initialize it randomly with some distribution, maybe normal distribution. And then we apply some algorithm on the training data, which is called learning algorithm, for example, gradient descent, or that is backpropagation. And then we iterate it until we find we have satisfactory accuracy on the training data. And of course, this is not all. Like, you have 3 types of data: training data, testing data, and validation data. So we will look into this because it will be helpful to understand how you actually train a model, and we will look into examples. So for recap, this is basically, we saw that what a perceptron is, how it works, and we saw activation functions and their need. Why do we need an activation function? And we understood what learning in context of neural network means, and we saw a few examples. So that's what we did in this lecture. And in the next lecture, I will describe this algorithm, gradient descent, and we will understand various types of learning. So the 3 that I mentioned, supervised, unsupervised, and reinforcement, we'll look into like a bit more, a little bit of detail in them. And then I'll show you some Python examples, including the example number 1, that how you train it. And at least for the next lecture, we won't be using TensorFlow. We are just going to build it from scratch. And maybe I'll live code it for you, or show you the code that, okay, how you can implement it from scratch. And you will also have the same thing on your assignment, first assignment, which might not be graded, but it will ask you to implement all of these things from the new perceptron to this algorithm from scratch. So yeah, that's our goal. So it's not a time, but yeah, I'm done with this.
So Hidayat, so what is the plan? So as per our schedule, the next lecture was going to be actually doing an example, a few examples on Z3. New neural network example, starting with the simplest one.
Yeah.
I mean, we can even do some other examples too. But are we sticking to that schedule? Correct? Yeah.
Yeah, we can have Z3. I thought that you had the Z3 tutorial already, but yeah, we can do that.
Initially, I had it. I mean, we can do it either way. Okay. So since maybe you could do that. We could. I mean, the motivation for doing that Z3 was for those that that do not have in the audience logic background, to give them some examples, not necessarily neural network examples, some basic.
Yeah, so I think we can have a Z3 tutorial next lecture, and after that we can.
I'm going to pose that question to the audience. So I really don't know how many are seriously interested in taking the course, and how many among them really care to want to, are basing their decision on if they are undecided, if that would help them to make the decision, I would do that. So at this point, I know there are only 9 people here besides the 3 of us. How many of you, and I'm assuming that these 9 will have are serious about taking the course. So since there are only 9 people, how many is there a show of hands as to you want Z3? How many of you would like to have Z3? If that could help you to make a decision of your wanting to take the course. This is a question to.
So, some of you can unmute yourself and just say.
So I attended the model checking.
There is also an overlap between here and model checking.
So most of the names I see, they were also present yesterday in the model checking.
Okay. Okay.
So we already saw Z3. Yeah. Maybe
yeah,
one or two did not see the Z3 yesterday. Maybe who didn't.
I think that would be a good question. So is there somebody that has not actually seen, some among the 9 people that are attending today that are did not see the Z3 tutorial in the model checking course? Okay, there is Ashish Sinha who has not seen Z3. So Ashish, are you serious about taking the course and we would rather have a Z3, a demo?
You can go ahead with, like, you can skip the Z3 demo for now. Like, I've still not made up my mind whether I'll take this course or not. So this course is like somehow not suiting me in terms of the expectations. So you
Okay,
can skip the Z3 demo. Yeah.
okay, fine. Thank you. Yeah, then I guess that's we can maybe we still want to give a Z3 demo to see what it is that it can do. That, but that doesn't have to be rushed into. Okay, so you continue with your with the introduction to neural network. Next.
Yeah, sure. So is there any question like about all this that we discussed, or?
Yeah, so I have a, so when we say that we want to minimize the cost function,
Yeah.
so are we basically, so how are we defining the cost functions? Is it like we are taking the sort of the difference between the expected and predicted and then averaging the difference, and that taken as a function of the weights and biases is the function we want to minimize, right?
Yeah, true. So just look at this example. So let's say the weight is W1 here, W2 here, W3 here, something of this sort. Okay.
Yeah.
So given one actual input, so as that's why I told you that we have the input with us. So suppose this is 0 0.5, 0.6, and 0.4. So what is the output? So if this is W1, so you will have 0.5 W1 plus 0.5 W2, okay? And you apply some activation function on it and so on, right? So all of the output here is a function of W1 and W2.
Hello? Hello?
Hello.
Hello? I can't seem to see.
I think he lost connection.
I see. Okay.
No, I don't think we lost connection. Maybe Hitar's
Yeah,
Hitar was kicked out. Okay, maybe he has a internet problem on his side.
yeah.
Okay, so we'll have to wait. I have his number, so let me call him. Hitar, what happened? Ah, okay, fine then. So we will wait. Yeah. Yes, he has a power issue at his end. So we will wait for 30 seconds, 30 to 40 seconds. He thinks that he can make some alternative arrangement. Let's pause for a moment. So while we are waiting for Siddharth, I have a call from Siddharth. Let me see. Yes, Siddharth. Okay. I'm seeing you. Okay. Yeah, he's joining. Maybe I'll have to make him a co-host again.
Hello. So I'm sorry, I had some like power outage here, so my computer suddenly got turned off.
Yeah, that's Indian, no?
Okay, so can you? Okay, so I guess Diganta asked question, right?
Yeah.
Yeah, so I was asking you. Okay, so this output that we get here, it is basically 0.5 W1 plus something, let's say 0.5 W2. And similarly for all of these things, like, so for all these weights, you will just multiply with these numbers and add it up. So what you get here depends on W1, W2, W3, W4, all these weights and the biases and the activation function. But the function, so ultimately what you're going to get is just the function of weights in this layer, right? Same for this thing. And when you apply it again you will get the same thing. This, all this output is basically a function of these weights and biases before this particular layer. So in the output layer, all these weights and biases will play some role to define this output that we get here.
Right.
Now, this output, you subtract this output from the expected value, and then you get this thing. So this 0.6 here is basically the summation of all these things. So we treat them as variables. We don't fix the W1, W2. We treat them as variable, and we get this thing, and then we take an average over all these, all the training examples, and that's how you get your net cost function. So this cost function basically is that. So you take average over all the training example. And because each example has the numbers here and there are numbers in the output, so ultimately what you're going to get is just a function in weights and biases. Okay.
Right.
Now,
so here CIWB is right. Okay, I see. Yeah. So
yeah.
it's,
So
it's
now,
basically the loss for a particular example, and we're taking the average over all examples that we have.
true. So because we don't, so what we don't want is the network should not readjust it for just one example. And then what will happen, it will never work for other example. It might not work for, there are some learning paradigm in which we do this thing, trained by one example, but at least in supervised learning, we don't do that. So we have batches and we do this. And then what we want is, so what we have is that the current state of the perceptron or network, sorry, neural network is just the sum assignment of these weights and biases, okay?
Right.
So if you assume this function is plotted, if suppose there are n, suppose total capital N weights and biases, so it is plotted in n dimensional space, then you have just one single point, right?
Right.
You just one single point. So what you want is that from that point, you want to walk so that you reach the minimum of this function or close to the minimum, local minimum at least. That's what gradient descent does.
Right. So in a sense, the function depends on the set of training examples that we're taking.
Exactly. And the structure.
Yeah, and the structure.
Yeah, and yeah, activation function plays the major role here. So that's what makes it all interesting. Otherwise, okay, so this is one thing which I think we can discuss because we have few minutes left. So I told you that if you use linear activation function, then multiple layer will collapse into one single layer. Can anybody just see this? Why is it so?
Yeah, you could, well, I guess you could plug it in, no? You could just...
It becomes a composition of linear functions,
Yeah,
sort of.
it's a
Right?
composition.
True, and that's all. That is basically, so there is no deep learning in a when you have a linear activation, because all the layers can be collapsed into one layer. So that's why we want something non-linear, and non-linear functions actually work. And this is what a brain does too. So if the threshold thing is basically non-linear, so it's 0 or 1 depending upon whether the total input is beyond the threshold or not. So yeah, that's the principle. Yeah. So any other question? Anyone
So
else?
I mean, just to like So the choice of the training example itself would really influence the entire
Yeah, so
function and the
that's,
minimization, right? Then
yeah, that's very important. So training data. So what we do is, you might say, if I give it in a particular order, then it might not actually be good. So usually we randomize the ordering, and then we apply again, then we again randomize it so as to include all the examples properly. And expectation is that on an average, on any example, it will the after training, the output will be very close to the required output. So training data is like, of course, the training data is the most important part. Like if you just train the training data, everything changes because the model changes, right? Because
right.
the behavior is not the same now.
Right.
Yeah. Anything else? So anybody else has any questions? So I'll wait for 2 or 3 minutes if there is any. Otherwise, we can end this. So if you have no question, then you may leave. If you have any question, then you can ask or stay. Yeah. I'll wait for 2 or 3.
You know, one comment I had was that I mean, this is leading to a question that will be covered as part of gradient descent. For any given set of training data, I mean, you already made the comment that it's very important. The choice of the training data very much depends on how well it behaves. Okay, but the requirement that they'll have to be differentiable, the activation function. The motivation for that is because of the way that the optimization, the optimal solution is for the weights is worked out by looking at the gradients, the change, the differential of W with respect to the difference in the error, correct? So that's why it's the difference,
yeah,
you differentiate that, you know, and you keep moving in that direction. And, you know, you showed that squiggly arrow. So, but the way it is done is by computing the differential, okay, and then adjusting. And then that moves you towards the optimal solution. And that's why you require that the activation function be differentiable in at least segments.
Yeah, so that's what the thing is, that we want a function so that we can differentiate it. And ultimately our task is that how should I tweak the weight so that it decreases. So that's the thing. So we will look into it, all of it in detail in the next lecture. Yeah. Okay, so I think there is no question.
Yeah, if there is, since we have 5 minutes, let me, can you, I mean, when I do share, I mean, this is nothing related to DNN. I'm going to switch over to a solution for the
okay, so
okay,
so I'll stop sharing that.
Just show. Okay. Yeah, can you see my screen?
Yeah.
Actually, I mean, Zubin has a solution, actually two solutions, which some of you, I don't know, we didn't not get to Sudoku. You know, he didn't get to discuss. He has already written programs to generate solutions for the Sudoku thing, which we, you know, maybe he'll get to show that eventually. I'm also thinking, we're also thinking that maybe I should find this as an assignment, okay, for Z3 as an Z3 exercise. But nonetheless, each of these constraints can easily be expressed if you view these as variables. Okay, you can view, you can encode this as a propositional problem. Okay, that is one. Or you encode. I mean, I had raised this question. You use arrays as with numbers, actually, you know, then, and you express each of these constraints that I had listed in there. And you can do that as if you're allowed to use quantifiers, then each of these constraints can be expressed in this as quantified formulas. So the whole formula whose satisfiability you will have to check in order to find a solution would be a conjunction of universally quantified formulas. Okay, so each of them says if for all I and j indices, for example, the first constraint, it says that it has to be, the elements have to be between 1 and 9, and that every number should appear exactly once can be expressed like this. Okay, that is for every row I, if your j, if any distinct j1 and j2, j1 and j2 is not equal, then they'll have to be different. Okay, so you could express these things like this, and this can be used as a template to generate unquantified the overall constraints in unquantified form. Or the interesting thing is you can actually this, as long as the quantifiers, there's no nesting of quantifiers, all of them appear only at the outermost thing, even if they are inside subformulas. For the theory of mixed theory of numbers and arrays, this is solvable as long as your constraints are in a fashion that that this satisfies. Like you see, each of these constraints is an implication which says that if some condition on the guards hold good, then some condition on the elements of the array must hold. Okay, so these kind of forms, so you can only have guard expressions, expressions on the indices in the guard. Okay, as long as you have it like this, even with universal quantifiers and subformulas, this theory is decidable. And actually Z3 supports it. Z3, that is, it's a known result that this one is decidable, and solvers support that. So in principle, you don't even need to eliminate these quantifiers. You can type these things in this form as they exist here into Z3, and it should work. I'm assuming that Z3 is implementing that decidable algorithm completely. If so, this should work. So that would be an interesting exercise for you, for one to try out on the side. Okay? Yeah, that's one comment that I wanted to make. Okay. Okay. So I will publish this as well. Okay, and if one is interested, one can try it by typing it into Z3 to see if it gives the solution directly with quantified formulas. Okay, so if there are no questions, we will end this session. So I'll wait for a few seconds. Hello? You guys there?
Yeah.
Okay. So are there any questions? If none, then I will stop sharing and end the session. See you next week. Thank you. Bye-bye.